Okay, well, another good Monday for programming paradigms. Now remember, what we're trying to do is solve the critical section problem. And we said that the way we were going to do this is we were going to make several attempts, and with each attempt we're going to introduce some analysis tools. And the first attempt was one where we forced the processes to take turns. So we had this variable named turn that was initialized to 1. And what did we find out about that solution? Remember, it was we had it used an await statement. And how did we implement the await statement in actual code? Do you remember what we used to implement the await statement? A while loop. And what is, yes, it was a while loop. And what are those? The purpose of that is to lock out the process from getting past that point if it should not. And so what are those things called? Yes, it is yes, that was part of the pre-protocol. But the loop, the actual loop to implement the await statement is called a what? A spin lock. Those are called spin locks. And so while, when he did his pseudocode, he had await. Well, the way we do it in the code is we have a loop. Well, we actually looked at the code a little bit yesterday when we did the demo, but here it is on the slides. This is algorithm 3.2 in C++. You notice at the top here we have global variable n, which is an int, and also global variable turn, which is an int. N is initialized to 0 and turn is initialized to 1. N is the global variable accessed by the application itself, and the turn variable is the one that is controlling the access to the critical section in the pre-protocol and post-protocol. So here we have void p run. So this is the code that process p executes. It has a local variable temp, and then it goes for int I gets 0, I less than 5, I plus plus. Actually, we actually started off with the for statement being I gets 0, I less than 10, I plus plus. And then we have a random delay, and here's the pre-protocol with the await statement, which is await turn equals 1, is implemented by this spin lock with the while loop. While turn is not equal to 1. Do nothing. And then the critical section temp gets n gets temp plus 1 with a random delay in between to try to force interleaving. And then the post protocol is turn gets 2. And then on this next slide we have the same code for Q, except it's the mirror image. The loop runs 10 times again, and this time it's the await turn equals 2 is while turn is not equal to 2, do nothing. And then the critical section with temp gets n gets temp plus 1. And the post protocol being turn gets 1. And then we have the usual simple main program here. We set up P and tell it to execute P run. We set up thread Q and we tell it to execute Q run. Then we do P.join, which forces main to wait until P dies, and then main executes Q.join, which forces it to wait until Q dies. And so whichever one dies first, it doesn't matter. After the two joins, we know that both of them have terminated, regardless of which one terminated first. And then our output, the value of n is, and then the value of n. The next thing we want to do is look how it's done in Java. Now, here is a technique. This is going to be a software technique, software design technique that we're going to have to use when we implement these algorithms in Java. And here's the problem. The problem is that in Java, both process P and process Q must execute the same run. Now this is in contrast to the flexibility of concurrency with C++. So here we see the code that process P is going to execute, namely prun, and notice that the while loop for its spin lock is while turn is not equal to 1. And furthermore, in this slide we see the code that process Q is going to execute, namely qrun. And you see its spin lock is while turn is not equal to 2. So the code that P is executing and the code that Q is executing is different. The problem is that in Java, both P and Q must execute the same code, namely run. There is no way to distinguish prun and qrun. There's just one run that both processes must execute. So how are we going to solve this problem? The answer is that we are going to assign each process a process ID, an additional attribute that is not necessary in the C++ code. So here is the beginning of algorithm 0302.java. Notice that we have the usual n initialized to 0, which is an integer, and turn initialized to 1, which is also an integer. And now both of these attributes are static. So now, do you remember what the word static means in Java? It means there is one per class instead of one per object. In other words, both processes access the same single n and the same single turn. But notice here that there is an additional attribute, not in the C++ program, named process ID, which is of type int. And then the constructor for the class has a single parameter, and what the constructor does is takes that parameter and it initializes process ID to that parameter. So let's take a look at what the main program does. And so here the main program instantiates P as a new thread, and it passes as the parameter a 1. And so therefore the process ID of process P is 1, and then Q is also instantiated, but this time with a process ID of 2. And then P.start executes and Q.start executes. So now what does P.start do? P.start creates the process control block, points the program counter to the first statement in run, and puts it in the ready queue. And then the same thing happens for Q. So now let's take a look at the code that executes when each one of these executes its run. So here, now notice there's not a run for P and a run for Q. There's only just a single run. And so we have our local variable int temp. But now look, the first statement in run is an if statement. And so we say if process ID equals 1. Well, if process ID equals 1, that was the process ID that was given to process P. So therefore P will execute this code in the truce part of the if statement. For int I get 0, I less than 10, I plus plus, try random delay. And now notice that it executes while turn is not equal to 1. And then notice that its post protocol is turn gets 2. On the other hand, the else part of the if, shown in this slide here, so else if process ID equals 2, well, that's the process ID for process Q. This is the code that Q runs. So we have the same for loop for int I get 0, I less than 10, I plus plus, random delay. And now, if process Q will execute while turn is not equal to 2, and then its post protocol will be turn gets 1. So that's how we solve the problem of having only one run needing to be executed by both process P and process Q. We give each process its own unique process ID, and then depending on which process is running, we execute the code for the one or the code for the other. What we have is class algorithm 0302 extends thread, so we've got some concurrency going here with processes. And our global variables are, again, we've done this one before, static volatile int, n gets 0, static volatile int, turn gets 1. Now what does static mean?
It's
one per what instead of one per what?
One variable per class.
One instance. One instance per class instead of? No, instead of one per, what's the other? One per class instead of one for each what? Each object or instance. Yeah, each instantiation. Yeah, okay? Is everybody with me? So it's one per class instead of one per object. Whereas in an attribute, if an object has an attribute, that attribute is one per object, per instance. Are you with me on that? Per instantiation. Yeah? Okay? So because both of these objects, they want to share the same one. If they each had their own copy of it, then there would be no communication. Do you see why we have to make those static? Okay? And then we remember what volatile is, right? We remember what volatile is, right? Maybe you should go back and look that up. You know, you would think that it would be something about changing, but volatile doesn't mean that in Java. Every statement is translated independently of the other one, so you don't optimize away the what statements. You don't optimize away the what statements. The compiler does not optimize away the what statements. The loads and the stores. Remember that? What does load? Load takes information from where to where? CPU to memory or memory to CPU? Load.
CPU to memory.
CPU to memory, and then you see my expression, and then it's yeah. Load. You load from memory to the CPU. You store from the CPU to the memory. The CPU is the processor. Are you with me? This is really important. You need to know this, because this is common in all instruction sets at the processor level. All right. So load is from memory to the processor. CPU store is from this processor to memory. Okay, and so volatile means that every single statement is translated with the load and the store. Every assignment statement is translated with the load and the store. Those statements are not optimized away. See, the compiler won't optimize them away, because otherwise then your analysis might be incorrect. Does everybody see how that works? So you should, as a rule, everything that is shared should be volatile. Because otherwise the compiler could optimize it away and your analysis would be all messed up. And now, you guys, so not only do we have this, but now what else does class algorithm 0302 have? It has a what? A process ID. And what is its type? Integer. Are you with me? This is how we're going to solve the problem of having two different. It's because, look, what if you want to have two different processes do two different things? Well, but they're executing the same run. So how are you going to, you see what I mean? You see what the problem is? If you want to have different code for one process compared to another process, you're going to have, but they're both running the same code. They're both executing run. So how are you going to do it? What you do is you assign a process ID to each process. And then you test for that process ID in the process. Now tell me, is this process ID static, yes or no? Is it static, yes or no? No. So there's one per what? So each object has its own process ID. Now, is everybody clear on that? Okay. And furthermore, here's the constructor for this class. And how many parameters does this constructor have? One. It's an integer, PID. And what does it do? Process ID. The attribute gets PID. Everybody see how that worked? So here's what happens. When we do, it's kind of interesting, isn't it? In the code here, when you say p1.start, what does that do? P1.start tells the operating system to construct the what block? The what block for that process? Tells it to construct the what block? No. Starts with a P. The what block? Come on. The process control block. The process control block. And what does the process control block contain? The values of all the variables, and furthermore, a pointer to the what? What's it called? The program counter, which says what? What does the program counter is stored in there, and what does that tell it? You know, when we did the state, actually, you know, when we draw the state here on here, that's a little mini. I take that back. Never mind. I was going to say something that was not accurate. But the program counter points to what? Not which process is next, but which what? Close. Which instruction is going to execute next? Because what is a process? Tell me the definition of a process. Uh-oh. Well, come on. What's the definition of a process? Oh, come on. Come on. What's the definition of a process? Anybody? Please tell me what the process is. I have failed. Okay, a process is a program during execution. Are you with me? Okay, everybody all together now. What is a process? Program during execution. Okay, a process is a program during, and how do you suspend if a process is a program during execution and it's executing? How do you suspend its execution? You have to store its what? Its state, the state of the execution. And where is that stored? In the what? Process control block. And then what is it? So start creates the process control block for that process, initializes all the variables to what their initial values are, sets the program counter in that process control to be the first statement to be executed, and then it puts it where? And then it puts the operating system puts it where? In a what? Yes, thank you. It puts it in a ready queue, right? And the ready queue, and then once it's in the ready queue, what will eventually happen? What will eventually happen? What will select it to be executed? What will pick from the queue and decide? The what will actually pick from the queue to decide? The operating system will. And the operating system has a scheduler. And hopefully that scheduler is what? Has what property? Is fair. Yeah, hopefully that scheduling is fair. You got to have a mental picture of where all of this stuff is. Are you with me on this? You got to have this mental model. Okay, so now, Shane, to get back to your question, where does run come in? Start does that mechanics. It does all those mechanics of getting the process control block, putting it in the ready queue, and then what happens is the program counter points to the first instruction in run. And then when the operating system eventually gets it, schedule it to run, the code in run executes. But see, we never call run here. We call start, and then the operating system, it's the Java system, the Java runtime system will execute the run, and when it creates the process control block at the very beginning and puts it, the program counter points to the first statement in run, which in this example is what? For int I get 0. So it does I get 0, boom, boom, boom. But then it comes through, but then it might get timed out. It might get interrupted.
And there can always only be one run.
The question is, there can only be one run in Java code. Yes. Yes, there can only be one run. So what we do is, if we want different
processes to execute different code. What you could do is, in the extreme case, and it actually might be convenient to do this later on when you do the one of the projects, software projects, it might be convenient to just have one great big if statement at the top and say, if the process ID equals 1, do all of this. Else, if its process ID is 2, do all of this. So I mean, in essence, you know, that's how you have one run for one and another one for the other. Or in this case, we can intersperse it, being clever like this, you know. Okay, so to show you then that this, in fact, you know, let's do the demo. That was algorithm 3.2. This time, okay, so now we have to do our demo. Okay, so here's our demo. And let's, actually, I think we saw the code on the overhead there, so we don't need to inspect it here. But let's go ahead and just run this, see what happens. Ah, did you see how that worked? But now, as before, what did it do? 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 8, 9. And again, we can illustrate starvation by going in here. Oh, this might be more difficult because I would have to change it for 1. Yeah, I don't think I want to mess with the code. But anyway, everybody see how that worked? Now, what we want to do the rest of this time now is go through some more attempts. And we're going to use the analysis tools that we learned last time for, and what was the problem with this one, with this first attempt? Do you remember? What are the 3 things that a successful solution has to have? What's the very first one? The one that's most important that we always start with, kind of. Say it again? That's kind of, well, yeah, the answer was it terminates. Yeah, that's part of one of them. But yeah, deadlock free is the second one. What's the very first thing that we want to not have? We don't want them to be where? In the CoSc at the same time. So what do we have to have? What's that called? Okay, we got to have mutual exclusion. That's the first one. The second one is what? Deadlock free. That's correct. And the third one is what? Starvation free. Now, which one of those 3 we analyzed this first attempt? Did it guarantee mutual exclusion? Yes or no? Do you remember? It did. Was it deadlock free? Yes. But the problem is, if one of the processes got hung up in the non-critical section, what could it do? Starve. Are you with me? So that failed. It's got to do all 3, right? Now, so here's our second attempt. In our second attempt, P announces its intent to enter its critical section by setting want P to true. Now let's jump ahead to this code. Look at this. This is algorithm 3.6. Now instead of having a turn, we have a want. Right? So want P is, both of these are Boolean, and want P is initialized to false and want Q is initialized to false. Yeah? And then, and what this represents, what want P represents is whether or not P wants to enter his critical section. So check it out. Here is the code. You have the non-critical section, and then what do? P in P2 says await what? Want Q equals false. So why would he await for want Q to be false? Because for him to get into his critical section. Why would he want to wait? Because what this means, if want Q is true, what does that mean? Q was what? Wanted to get in first, right? Okay. So he awaits want Q false, and then so this could be implemented with a spin lock. Are you with me? And then what happens is once Q gets in and gets out, the last thing that Q does after his critical section is sets want Q to false. So then once Q in his post protocol statement sets want Q to false, then P2 is free to get in. So he awaits want Q equals false, and then he sets wants P to true and then gets in his critical section. And now that he's in his critical section, he sets want P to false. So the idea, so here's the idea. Let's go back and take a look at the idea. P announces its intent to enter its critical section by setting want P to true. All right? P announces its intent. And then Q waits until P does not want to enter before Q announces Q's intent to enter Q's critical section. This description is flipped from the one I started with. And then when P exits its critical section, P sets want P to false as P no longer wants to enter. So do you see the idea there? What you're doing is you are announcing your desire. And the other process is waiting on your desire, for your desire to be fulfilled, and after it's filled, then it can go ahead. Okay, and so here's the code. All right? Now, what do you think about this? What do you think about this code? Yeah, question?
What if you got into P2 and then you did P2, so the next would be P3?
Well, if you're in P2, the next one could be P2 again.
Yeah, well, what I mean is, what if you
What I'm saying-
succeed in your await on P2,
Yes.
and then times out and goes to Q, and then goes all the way through, and then it succeeds on Q2, because P3 never happened yet.
Right. That is really good analysis. That's exactly the way you need to think about this. And that's exactly what we're going to explore. And that was a good point. Does everybody hear his analysis there? Let's take a look. Let's take a look. First of all, I want to show you that this is in fact starvation free. I think it's starvation free. Because look, here's an analysis of starvation. Suppose P is stuck at P1. So here's P1, right? Here's P at P1. That is not making progress. Okay, and suppose that want P and want Q are both false because they start off to be false, right? They start off to be false, and suppose P starts up and he's here and oh, he's just kind of doing, getting hung up here, right? What can Q do? What would happen if Q is eventually selected to run, assuming weakly fair? What will it do? Get through its non-criticals. What will happen when it does await want P equals false? Well, what is want P? False. So what can it do? What would it do then? Do want Q would get true. Are you with me? And then it could do its what? Critical section. And then it could set what? Want Q to false. And then while this is still stuck, it could come back to here to the non-critical section and then do what? Want P equals false. And then what? Do Q2 and critical, and then he could do it as often as he wanted. Doesn't have to take a turn. Do you see what I mean? He doesn't have to take. And furthermore, if he ever got stuck here, and this guy ever got off here, this guy could do what? 2 or 3 in a row by symmetry. Does everybody see that? So analysis of starvation. The following scenario is still possible. Q1, Q2, Q3, Q4, Q5, Q1, Q2, Q3, Q4, Q5, Q. Yeah, Q could just keep going, and there's no starvation. Does everybody see that? Conclusion: the second attempt is starvation-free, but now you have a scenario that might give us a problem. What about mutual exclusion? Oh, first of all, let's think about mutual exclusion. Did you think that it was mutually exclusive or no? Do we have mutual exclusion? We're going to consider this abbreviated diagram. Remember how we abbreviated the diagrams? We don't need to put in the statements for the critical section and the non-critical section. We just do the protocols. Okay? So this is await want Q equals false, want P gets true, want P gets false, await want P equals false, want Q gets true, want Q gets false. So this is, so consider this abbreviated diagram. And let's do an analysis of mutual exclusion. Starting at state P1, Q1, false, false, show state transitions that get to state P3, Q3. Is that possible? If we ever get to state P3, Q3, what will happen? If we ever get to state P3, Q3, what will happen? What will that be? What they will both be where?
It's like
They will both be in their critical sections because this is the post protocol. Are you with me? Do you think, here, let's see, is it possible to get into, here we go. Are you ready for this? Is this focused? Okay, check this out. If we start here, and our initial state is P1, Q1, P1, Q1, P1, Q1, false, false. Now, I think it's not going to guarantee mutual exclusion. Can you see how that happens? If P executes, what do we go to? If P executes, what do we go to? P2, Q1, false, false. Then if Q executes, what do we go to? P2, Q2, false, false is right. And then if P executes, what do we go to? P3, Q2, and what was it? True, false? True, false. And then if Q executes, where do we go? P3, Q3, what? P. Oh, can Q execute?
If it's awaiting one P false.
But it starts as false. They both start as false.
But then it gets set to true. Well, it's in Q1, right? It's execution already passed.
Oh, this is a good discussion. What?
It got in before the gate was closed.
But Q2 is next, which means it's in Q1, doesn't it?
Well, which one of these transitions do you think is impossible?
What you're about to draw, wouldn't Q loop? If Q executed, wouldn't it loop back to itself?
Would it? What is Q? It's Q2. Q2 is an assignment statement.
But that's,
No. Q2 is an assignment statement.
I don't like how this diagram would work. Okay.
No. Are you with me? This is the statement that's about to execute next.
Yeah.
Can it not execute? So maybe your question is one of these.
Well, no, I thought that if Q2 was going to execute next, that meant it was in Q1 currently. Is that not accurate?
Okay, let's review what exactly these state diagrams mean. What this is this is the statement in P that's going to execute next, and this is the statement in Q that's going to execute next. These are program counters that point to the statement that's going to execute next, and these are the current values of the variables. So the state is a list of the variables and their associated values, right?
Yeah.
Now, let's make sure
So it's kind of somewhere in between Q1 and Q2.
well, no, there's no, now wait, let's not be fuzzy about somewhere in between. Let's make sure that, because each one of these is atomic. Are you with me?
Right.
Each one of these is atomic. We know it satisfies LCR, so, each one of these is atomic, and that's our assumption. So I think that each one of these was valid, and it's very defined as to what the state is, and what the next state will be if that statement executes. Are you still having a question about,
No.
are we good? I mean, are we good? Okay, so now if Q executes, what's going to happen? So is everybody? Okay, so now if this executes, what's going to happen here? P3, Q3, true, true. Oh! And what's the deal? Is it deadlock?
No.
I don't think it's deadlock. It's not deadlock. What is it? P3, Q3. So look. So P3 is about to execute next, and Q3 is about to execute next, but those ones that are about to execute next are the post protocols. That means they are where? They are both where? In their what? Critical sections, because this is the abbreviated diagram. Is everybody with me on this? Look, they are about to see, look here, in this figure, it's P4, Q4. Sorry, it's P5, Q5, because those are the statements that are about to execute. So therefore, they are in their critical sections. Is everybody clear on that? So what's the problem with this second? Oh, here it is. Here's the same thing that we did, all right? Fragment of the state diagram for the second attempt. And so our analysis of mutual exclusion is conclusion. The second attempt does not enforce mutual exclusion. Well, wait a minute. How can we fix this up? How did they get in? Let's go back to the code. Let's go back to the original code. How did they get in? What allowed them to squeak by? P, Q, and then PQ. How did that allow them to, can you see a way to not let them get in? We can maybe fix this up a little bit. Instead of having await, want Q equals false, and then want P gets true, what was the problem? We did each one of the awaits, right? So, what's another attempt?
You want to get false?
Well, flip them. Flip the order. Are you with me? So look. So our third attempt is to switch the order of P2 and P3 from the second attempt to get mutual exclusion. Right? Oh, but now you're shaking your head. But don't you think this will get us mutual exclusion?
Yeah.
You do think it'll get us mutual exclusion, but do you see right away what the problem is? This will guarantee mutual exclusion, but what's the problem? Yeah, there's a possibility of, I think there's going to be a possibility of deadlock. All right? So now, so how can we get here? Analysis of deadlock. Starting at the state P1, Q1, false, false, show the state transitions to get to a state P3, Q3, true, true, with no possibility of progress. You see what I mean? So one is at its await, and the other is at its await, and there's no possible. So now, how can that happen? Here. Actually, I shouldn't have erased this, huh? I think if they just, it's different states, but. Yeah, so here, let's do it real quick. So here, if we start here, and we're going to start with P1, Q1, false, false, right? P1, Q1, false, false. And then if P executes, if P executes, what's going to happen? Oh, this is not abbreviated. This is going to be ugly. So if P executes, what will it be? Come on. If P executes, come on, you guys.
P2, Q1, false.
If P executes,
P2,
P2,
Q1,
Q1, false, false. And then what? And then if Q executes, I think if we just enter, if we go back and forth, right? So this will be what?
P2, Q2,
P2, Q2, false, false. And then if P executes, then what? P3, Q2, but now what? True, false. And then if Q executes, now what will that be? P3, Q3, true, true. And now what's the problem? Because if P executes, where will it go? Yeah, now if P executes, it'll go here, and if Q executes, where will it go? And so do you see that this is the state transition diagram that shows us the deadlock? See how these state transition diagrams work for us? Okay, so P2, yeah, he started with P2 in the figure here. He started with this one. Boom, boom, boom. Anyway, are we good? Does everybody see that that's the problem? That's a problem. Okay, so the conclusion, darn, the third attempt is not deadlock free. Here's our fourth attempt. Now this fourth attempt is really kind of unbelievable. Incredible. Seems ridiculous. How could you do this fourth attempt? Watch, look, take a look at the code. Now look, watch this. First of all, we're going to go back to the want P and the want Q, right? Now what we're going to do is we're going to keep. Now, what did we do on our third attempt? We had didn't we have we had the await, or we set it to true first, right? We set the want P to true first. Now what we're going to do is we're going to do this. We're going to say want P gets true. Now watch this, and then we're going to say while want Q. Now, so this is kind of like a spin lock, but it's not exactly a spin lock because what are we doing in P4? Want P gets what? False. And then what? Wait, want P gets false, and then want P gets true. What the heck does that do? It allows for interleaving between what? Between P4 and P5. Oh my goodness. And so if this allows for interleaving between Q4 and Q5, also. So where did that deadlock come? Remember where that deadlock came from? We were stuck where? In those await statements. So now instead of having an await statement, we're going to have a spin lock, but instead of doing nothing, we're going to just set want P temporarily to false and then set want P back to true again. So you say, oh, I will relinquish my desire to enter, and if you want to interleave here, you may, but then I'm going to reassert it before I go back. Do you see how what the idea is? Okay? And by allowing this for interleaving, it's now deadlock free because there's a way for the interleaving to happen so that the other one can make progress and it won't deadlock. So look, you guys, it does mutual exclusion, it does deadlock free, but look, now we have the hardest one, which is what? Starvation free. It's not starvation free because there's perfect interleaving that can. Here, can you see what could happen with perfect interleaving? Let's take a look at just take a look at the code. What's the code that would do perfect interleaving? They would both be in there while want P and while want Q, right? Okay, and so what would happen would be what? P4, right? Q4, P5, Q5, P3, Q3, P4, Q4, P5, Q5, P5, and they could just boom, 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 and then you could get starvation. Because even if it's fair, right? Because it's not that one process is not being held up by the operating system. They're both getting their fair share, but if they get it exactly one at a time, it's perfect interleaving. Okay, and here is the slide that shows. See, it's a cycle in the state diagram for the fourth attempt. It's P3, Q3, and then P3, Q4. So Q executes, then P executes, then Q executes, then P executes, then Q executes, then P executes, and you can boom, 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 boom. Right? All right. So now, with all that lead up, guess what? We are now going to display the solution, which is called Decker's algorithm. And guess what Decker's algorithm is? It's a combination of the first attempt and the fourth attempt. Now, what did the first attempt have in it? A variable called what? Remember the very first one? Well, turn, right? Whose turn it was. We force them to the turn. It's whose turn it is. now we're still going to have so we're going to reintroduce that variable turn, but now it doesn't mean whose turn to enter the critical section. It's going to be what? If you both are trying to get in at the same time, whose turn is it going to be to get it to break the tie? It's not whose turn to get into the critical section, it's whose turn to break the tie. Do you see the idea? It's whose turn to break the tie. So Decker's algorithm is a combination of the first and fourth attempts. The turn variable means whose turn it is to insist on entering if they both want to enter at the same time. And here it is. Check this out. Algorithm 3.10. Decker's algorithm. Look at this. We still have want P. So now we have, not only do we have want P and want Q, we also have turn. Want P is initialized to false, want Q is initialized to false, and turn is initialized to 1. So that's just arbitrary. Turn could just as easily be initialized to 2. Right? Now check it out. So, and we're going to, this whole thing is looped forever, right? So now, here's the non-critical section. And again, like before, we do want P gets true. See, I want to enter. P wants to enter. So the first thing P does is he says, I want to enter, so I'm going to set want P to true. But then, if want Q also wants to enter, now if want Q doesn't want to enter, what does he do right away from P2? He goes right away to what? P what? If want Q is false, so Q doesn't want to enter, what's the next statement after P3? P8. Are we good? And he gets in. But on the other hand, once he goes from P3 to P4, that means what? That means both want P is true and want Q is true. That's the only way that can happen, right? Okay, so, but now what happens is he gets to P4. Now whose turn is it to insist? So if turn equals 2, he does this. But if turn isn't equal to 2, what does he do? If it's not the other guy's turn, what does he do? He goes back to P3, right? And if it's still not, he'll keep going back. And eventually, what will happen? What I'm saying is, eventually, what's going to happen here? Eventually, what's going to happen is want Q is going to be false. Because what's going to happen is it's going to get false right here, and then he's going to await. Do you see how that works? Want Q is going to get false at Q5, and then he's going to wait. And so eventually and we can prove that eventually that will happen. And when that happens, he will get into his critical section. And by symmetry, the same thing works the other way. And so what happens is, here we do want P gets false and want P gets true, but in between these two things, we have this await turn. And it's symmetric. So there you have it, sports fans. That is the famous Decker's algorithm. And here is the idea. In process P, if want Q equals true and turn equals true, then Q will enter its critical section. And the proof of correctness of this is the next chapter. We're going to prove the correctness of Decker's algorithm in the next chapter. And one of your projects is going to be to implement this. But this is just a straightforward. Do you see how you would implement this in both C++ and Java? Could you do that? You could do that now if I ask you to, right? Because it's just translating this, right? This is a while statement. This is an if. And this await, how would you do this await? Yeah, that's a spin lock. Do the await with the spin lock. And here's the amazing thing. Now this isn't the only solution to the critical section problem. There are others, and the book describes them. We don't have time to get into all that, but the amazing thing about this whole phenomenon is that this whole thing can be done completely in software. This is a high-level software solution to the critical section problem. And it guarantees both, what are the three things? Mutual exclusion is the first, deadlock free is the second, and starvation free is the third. Are we good? Okay, good deal. See you tomorrow.